It is the most strange railway in the world. This is not for any kind of train. This is for boat, for ships. It's only one working in the world, system like this.
Many wilderness railways cross vast, flat terrain. But when they have to go up, it's a whole new world. Nothing grows, practically nothing can survive. So getting a railway to the top of a mountain is a tall order. Whew. At over 3,000 meters, the steep climbs up the sheer cliffs of the Bernese Highlands in the Swiss Alps are only accessible to mountaineers. You only have to look at this lofty wilderness to appreciate it's the last place you choose to build a railway. However, in the late 19th century, one intrepid train engineer not only took on this unforgiving terrain, he chose to build a railway up through 3 of its most extreme and iconic mountains.
Here we are, standing in front of the famous 3 mountains. The Eiger on the left, the Mönch and the Jungfrau. All 3 of them roughly about 4,000 meters high.
These 3 mighty summits have fascinated poets and artists for hundreds of years. But at the turn of the century, the majestic mountains also started to work their magic on the general public. As interest grew, entrepreneur Adolf Geyer-Zeller was determined to build a railway to bring these mighty mountains to the masses.
People want to see the mountain, and Adolf Geyer-Zeller, he was the man who had the idea to build this railway. He wanted to build the level to the top of the Jungfrau.
His remarkable achievement is the Jungfrau Railway. A railway that climbs 1,400 meters through a vicious wilderness of rock, ice and snow. The end of the line, Europe's highest station. Train controller Christopher Soothall knows all too well the challenges of building a railway here.
The weather can change within seconds, really. It can be from a summer 25 degrees here to a winter of minus 25, with extreme weather, high winds, thunderstorms, snowstorms, snow drifting. Today, we're lucky.
Instead of taking the weather on, Geyer-Zeller's audacious solution was to avoid it altogether. He decided to build a train that could climb the inside of a mountain. From the Kleiner Scheidegg base station at 2,000 meters, the initial 2-kilometer route is above ground. But incredibly, Geyer-Zeller then chose to dig and blast 7 kilometers of tunnels through the mighty Eiger, Mönch and Jungfrau mountains.
This was very difficult and very dangerous, you know. There was about 300 employers and 30 people died.
But, as tour guide Roland Fontenive is about to find out, although building a railway inside a mountain avoids the weather, it creates yet another seemingly impossible problem.
Now we go up to Jungfrau Joch, top of Europe, by the Jungfrau railways.
Geyer-Zeller was operating in a golden age of steam. But coal-powered trains and long underground journeys aren't a good mix.
You cannot go with a steam train 7.3 kilometers in a tunnel, you know. Then in the top everybody will be black, black face. The only option was to go by electric.
But when you're slap bang in the middle of a wilderness, 3.5 kilometers above sea level, finding an electric supply for your train seems an impossible challenge. However, Geyer-Zeller turned the wilderness to his advantage, creating another extraordinary solution.
He need to build hydroelectric power station before they could build the railway.
Gajazella built his very own hydro power plant, 15 kilometers from the railway, providing a dedicated and ready supply of electricity.
The technique, it's more than 100 years old, so we have brand new generators, but it's the same systems like at the start at producing electricity.
Fed from a local river, the power is generated by funneling its water down a whopping 160-meter drop.
This one is from an old generator, and the water from the river is falling like this, and then the wheel is turning, and so with this type we are producing electricity.
Over 4,000 litres of water per second flow through these wheels, feeding energy into the generator above.
As we said, in the upper part is the generator, and here you can see the high voltage cables. So in these cables are 6,000 volts, so we can touch them and it feels pretty warm, so that's the electricity we feel at these cables.
Going uphill, of course, it's just the power of the motors and the electricity getting the train up to the top. But coming down, the motor actually works as a generator, and it's actually generating electricity. 80% is reserved for its braking power, but the last 20% is actually put back up into the power cables. So in theory, you could say 5 trains down and we send up 1 train for free.
Electric motors drive a rack and pinion system that pulls around 5,000 passengers a day up the steep 35-minute climb.
Now we're coming up to the tunnel.
No matter what the weather.
When we go up in the winter, we didn't have to push the snow away, you know. It's always free, you know. And so you can go up 365 days in the year. I think that time their only choice was to build the tunnel.
During its construction, this hugely ambitious railway's costs doubled. But the industrious Gajazella had forward planned for a shortfall. Partway up his tunnel, he created a station and viewing platform known as IJsmeer, or Sea of Ice. As his workers continued to dig to the top of the mountain, trains would bring paying guests to this midpoint to marvel at IJsmeer's beautiful vistas, raising valuable revenue.
Wow, good. In the beginning, they had some mountain guides. They go hiking with the guests, so you could go outside. I think it's very nice view. You can see in the ice, in the crevasse, you see the crevasse of the glacier.
Today, this is no longer the end of the line for Roland and his fellow passengers. The impossible railway has one more mighty climb to tackle. All this work can create wear and tear that could see the crucial rack and pinion fail.
Here we have one of our drivers lubricating one of the trains.
To ensure nothing is damaged, engineers have developed a special oiling system.
These 2 tanks is about 10 litres of oil, and that will be enough for about 1,000 kilometres of this train to go up and down.
Every 50 seconds, the rack and cog are automatically sprayed with an 8-second burst of oil.
It not only lubricates the rack and pinion, the cog, but it also lubricates the wheels, so the track will also have less wear and tear. It is very essential that these trains are lubricated and this oil system works due to possibility of a derailment, which, of course, no train company wants to have.
Brilliant engineering ensures the Jungfrau Railway reaches the end of the line, 3.5 kilometers above sea level. Its passengers confronted with a viewpoint that would have been impossible to reach, but for the toughest mountaineers.
Wow.
Right now, we are on 3,571 meters. Yeah, the view is perfect. When people see the view, most people, they start to cry. What can I say? Before, only by foot you can come up here. This was something special for people.
It's a view Adolf Geyer-Zeller would never enjoy. He may have died before its completion, but his impossible railway has conquered this great wilderness.
Today, if someone said to build a train through these mountains, you would think they're crazy. But this happened. 105 years ago, they completed it. It happened.
The trouble with most trains is they only have one engine. So the longer you make them, the loco must take the strain.
Hello.
But if there's a need for speed, there's only so big an engine can be. The birth of our railways and the steam locomotive go hand in hand. For over a century, across the world, these iron workhorses graced our rails. But by the 1930s, in the UK, these mighty machines faced a seemingly impossible challenge. They needed to go faster. As rail journalist Tom Bright is finding out.
Passengers at the time wanted their trains to be faster, more comfortable and more luxurious. So they introduced more facilities on their trains, such as dining cars and luxury saloons. But that meant trains got heavier and therefore slower.
The once thriving rail networks were under threat from newer, faster road travel, and the rail companies were fighting for fares. The most hotly contested route was between the two great capitals, London to Edinburgh. To make this near 650-kilometre journey at speed in a steam train weighing several hundred tons would require a locomotive like no other. And in 1935, it was the A4 Pacific class that would change everything.
They brought improvements in speed and power that the world had never seen before. The A4s were the ultimate in express passenger locomotives.
Its designer was one of Britain's great railway pioneers, Sir Nigel Gresley. Gresley had already designed the legendary Flying Scotsman, an A3 class locomotive.
What Gresley did with the A4s was bring together all his existing ideas. In effect, the A4 is an A3 GTI, a souped-up A3.
The secret to the A4's power is the unique combination of innovations.
He was really pushing boundaries. With the A4s, he opted to have 3 cylinders. With 2 cylinders, the locomotive tends to wobble at speed. With 3, it's much more balanced.
Gresley's 3-cylinder formation produced smooth power, and the wheel configuration made the most of it. 4 small at the front, followed by 6 enormous driving wheels, giving 50% better grip, and 2 smaller rear wheels, which allowed space for a larger firebox. It meant more steam, more power, and so much more speed. After recent significant repairs, today a group of engineers and enthusiasts are firing up the Union of South Africa, one of only 6 remaining A4 super engines.
Needs just a little bit more, mate. About 3/4 full.
And it's a rare return to service for this 80-year-old powerhouse.
Basically, we're lighting the fire. So we've laid coal in there, we've put wood on top, and now we're using paraffin-soaked rags on top of that to get everything going.
Main priority is water's in the boiler. We definitely need water in there. Make sure it's fit to run, really.
Shut the top, please.
When you're pulling away, you've got to be very, very gentle with the regulator. It's got so much power, it will spin straight away if you gave it everything. Here, we're only, unfortunately, allowed to do 25 miles an hour. You're having to hold it back, really. It's such a powerful beast.
For today's trip, they're joined by the Union of South Africa's owner of 50 years, John Cameron. And it's an anxious wait, hoping that his antique train has still got what it takes.
That's one of my concerns, that it's working and that it won't fail. It won't sit down, as we say.
There are hundreds of rail fans hoping for the experience of a lifetime.
That sound you can hear is the singing that you want to hear, so you know the injector's on. Once you've got that, then you know you've got your injector on.
There's a lot riding on this mighty machine's historic engineering still working.
Well, you know, you've a lot of power at your command, so you've got to use it sensibly.
Trying to get a feel for the regulator. Shortening the cut-off so we don't need so much steam.
You always have to know your locomotive and know how it's going to respond, whether you're starting off, running at speed or braking. I mean, there's no two locomotives behave the same, even though they're the same class.
Gresley had created an engine of immense power. But before he could test it out, there was one more problem to overcome: the shape of the nose.
Gresley took his formative design into the wind tunnel. This is something that had never really been done on locomotives before.
The traditional flat nose was replaced with a wedge-shaped nose to decrease wind resistance, but crucially, lift the smoke and steam away from the cab. In 1938, equipped with this perfect blend of engineering, the A4's Mallard reached 126 miles per hour, becoming the world's fastest steam train, a record that still stands to this day. Gresley's A4 design easily outstripped his competitors in both speed and style. Passengers could now travel on the East Coast Main Line from King's Cross to Edinburgh in only 6 hours.
When Mallard broke the world speed record, then that gave the A4s another bit of added attraction, if you like. But I mean, the potential for doing speeds in that magnitude is certainly still there today. So when you're on a line like this, some people might think that you're just pottering along. But actually, there's just about as much skill required to drive carefully and efficiently at a lower speed, you know, to make the job go well.
And today's run has done the team proud. Gresley's super high-powered design achieved the impossible. The speed of the mighty A4 locos helped revive the railway, bringing passengers back on board. And his creation still continues to amaze to this day.
Union of South Africa really is one of the best. She is absolutely lovely.
If speed is the only goal, come on! The faster you go, the bigger the problems. Any curve is out of the question. Even the tiniest bump has to be ironed out. And then, of course, stopping can be the biggest challenge of all.
Uh-oh.
The Tularosa Basin in New Mexico is a vast, isolated wilderness. But it is also the unlikely setting for a record-breaking railway. Hidden in the depths of the desert lies one of the most extreme rail tracks on the planet.
We're at Holloman Air Force Base, New Mexico, at the high-speed test track, where we push the bounds of speed. And we use this, the most incredible railway in the world.
Built in 1949 to trial new aviation technology, this extraordinary 16-kilometer rail line pioneers extreme speed, propelling its rocket sleds to around 2,900 meters per second.
In total, we've broken the land speed record 7 times and currently hold it at over 8 times the speed of sound. It's no exaggeration to say we make history here.
But with the sleds covering the equivalent of over 30 football pitches per second, the engineering challenges are seemingly impossible. If the railway track isn't perfectly engineered, the consequences will be catastrophic.
Any deviation in that rail is an impact load. It's basically like a speed bump in a parking lot. And if you hit very many speed bumps at these ultra-high velocities, you will not survive.
The extreme range of desert temperatures means the rails must be pre-tensioned to avoid any expansion and contraction. The continuous welding along the 16-kilometer length ensures arrow-like straightness. But all of this is secondary to the most crucial engineering of all: the challenge of making sure each sled sets out and sustains a perfect trajectory.
This sled's going to be tested at Mach 4. In order to survive and maintain its path down the track, the sled has to be aligned to within a few thousandths of an inch. Failure to maintain that alignment could result in the sled exiting the rail. It could destroy the track. The way that we maintain that is we use a laser 3D tracker to verify its alignment.
With over 10,000 test runs completed on this phenomenal railway, the test track sled park is the resting place for speed machines once used to test vital areas, such as parachute deployment and pilot ejector seats.
So we've got the A10, F15, F16 here that all run down here at the track. Right here behind us, we've got the Sonic Wind replica. This is an example of the sled that ran down the track, specifically designed to see the factors affiliated with undergoing large Gs.
In the 1950s, the Sonic Wind No. 1 was piloted by Lieutenant Colonel John Stapp. His goal? To establish the effects of extreme acceleration and deceleration on the human body. In 1954, a 1,017-kilometer-an-hour run made him the fastest man on Earth. Incredibly, from this mind-blowing top speed, he was brought to a standstill in under 1.5 seconds, thanks to an innovative solution: a water trough braking system positioned within the track.
He basically underwent up to 40 Gs of deceleration during his last ride.
Battered and bruised, Stapp's mission was nonetheless an important milestone in improving safety for airmen and pilots. Today, unmanned sleds reach almost 10 times the speed of Stapp. Although this rail line is precisely engineered, the sleds themselves require a genius innovation to survive the brutal stresses of a run.
We don't use wheels because of the ultra-high speeds that we travel at. You simply couldn't keep the sled on the track. So what we use are slippers.
Attached to the bottom of the sled, the metal slippers are curved around the head of the rail. As the sled gains speed after launch, aerodynamic forces lift the sled from the rails until it's stopped by the slipper.
So once a sled takes off, it doesn't actually slide on the rail. It kind of floats. There's very little contact with the rail. A good example is if you ride a new modern roller coaster, it's a very smooth ride. But if you ride an old wheeled roller coaster, it's a really bumpy, rough ride. And that's exactly what the sled experiences out on the track.
For over 60 years, this game-changing railway has achieved what was once thought beyond the realms of possibility. And it seems, for the Holloman high-speed test track, the sky's the limit.
So the next goal is Mach 10. Just to put it in perspective, that's going from this point to the very north end, 10 miles away, in about 5 seconds. So anyone that needs to go fast, they look to the Holloman high-speed test track.
I believe this is the most incredible railway in the world. I wouldn't want to be anywhere else.
Imagine you're a growing industrial region that is desperate for a good transport system. But high groundwater levels make tunneling impossible. And a hilly terrain and a flood-prone river. Pour cold water on any plans for a traditional rail line. That's exactly the situation engineers were facing in Wuppertal, Germany. By the late 19th century, the booming centre had reached an all-time population peak of 400,000 and quickly needed an efficient mode of transport. But with its packed streets and uneven terrain, all but the most extraordinary railway would be impossible.
You cannot imagine Wuppertal without it. We need this noise. This is just like a melody to us, it's like a music.
The Wuppertaler Schwebebahn, literally Wuppertal's floating train, was opened in 1901 and is still carrying the local population through the seemingly impenetrable cityscape today. Including local guide Gisela Rohleder.
This railway is certainly one of the most unusual railways. It is in fact an ingenious design. Nobody could imagine to have such a masterwork of techniques here in our tiny town. It looked really futuristic.
This impossible railway is the brainchild of inventor Eugen Langen, who, unable to tunnel or disrupt the city streets, decided to put a monorail on top of the city's river.
It's designed for the city, for this narrow valley with no space. So it was possible to construct it rather all the way along above the river, not requiring any supplementary space.
Langen's design could straddle the river and nearby streets using a steel upturned V design, and so avoiding digging in the waterlogged land or demolishing areas of the city.
It has been constructed in a height of 12 meters with a steel frame having nearly 1,000 legs, something like a caterpillar.
Following the city's river was a brilliant solution, but threw up another challenge. The windy river route meant that a traditional monorail that rigidly straddled the track would not be able to cope with the centrifugal forces at speed. So Langen turned railway engineering on its head, flipping the cars under the line and giving the floating train's passengers a unique swinging ride.
When the train moves around the curves in the track, it has to swing. And it swings up to 15 degrees to the sides, depending which side we go in the curve. Just now, for example, we swing to that side, to the left. Now we go the other way around in the curve. And we swing to the right.
It's like riding a bicycle, but upside down. As you can see, it's quite easy to put it into a slight swing.
That ability to swing is essential to the Schwebebahn's success.
The vehicle needs to swing because you can make tighter turns and the force on the passengers is very small. The system is unlike any other system in the world.
This unprecedented flowing motion would have been impossible without some inspired engineering on the train itself. Today, project manager Markus Schawate is overseeing essential works on the Schwebebahn's vital wheels.
We are in the workshop of the Schwebebahn. They're doing some maintenance today. Now we have to maintain here the wheels of the new Schwebebahn, and we have to remove one wheel of this complete set. So these wheels have a maintenance period from about 200,000 kilometers. And then the wheel has to be changed, to be exchanged for a new one.
Positioned above the train, the design of the Schwebebahn's supporting bogie assembly, including its wheels, is unique. To appreciate this, you need a view you can't get from street level.
We are now on the top of the workshop, and we are actually above the track. And you see the bogies of the vehicles. You see gearboxes, the left and the right one, and in the middle the motor. The track is a normal railway track, as you see, and the wheel is quite different because the wheel has two edges. A normal railway wheel is different because it has only one edge, and there are two wheels on a normal railway system.
As the Schwebebahn operates underneath the single rail, this twin-edged wheel design ensures the train remains safely attached at all times. Throughout its history, this impossible railway has been at the heart of Wuppertal. The Kaiser himself travelled on board, along with thousands of commuters. And in the mid-century, one surprising traveller jumped aboard.
In 1950, we had a very particular passenger in the Schwebebahn. And this passenger was a little elephant baby, 3 years old and 650 kilos of weight.
With the circus in town, Baby Toothy's ride seemed a perfect publicity opportunity. But he didn't agree.
It started to panic after a few seconds because it was not at all used to the noise this train made. It smashed all the furniture and smashed as well the side wall of the train, so that there was a big hole in the side. And before reaching the next station, the elephant jumped out of the train into the river.
Happily, Toothy survived the fall and was undoubtedly more at home in the muddy waters of the Wupper. Today, around 25 million satisfied passengers ride the Schwebebahn every year. For Marcus, its incredible popularity means it's time to evolve.
Most of the trains are in operation since 1972. Each train covered about 2.5 million kilometers. So it's time for a change.
When the upgrade is complete, the new 31-strong fleet will mean passengers will have no more than a 2-minute wait for their train.
The increasing of this service is because of the number of trains and the new technology. One train can drive closer to the next train.
The charm of the old stock is undeniable. But the future is bright.
So we are now on the new vehicle, and you see it's much brighter and more friendly. The difference to the old vehicle is that the windows are bigger, and even the seats are a lot more comfortable. Yes, I've ridden it as a passenger, and it's quite beautiful, and it's very good.
Old or new, this groundbreaking railway is the making of this city.
Wuppertal without the Schwebebahn would not be Wuppertal. That would be something else. It belongs to Wuppertal since more than 100 years. That's one thing, Wuppertal and the Schwebebahn.
If you're an island city separated from the mainland, bridging waterways can allow rail supplies to flow, but can leave your vital rivers well and truly blocked. Keeping everyone happy in the city, hey, come on, can be an all but impossible bridging challenge. But one railroad in 1950s America proves otherwise. Staten Island in southwestern New York. Sandwiched between mainland New Jersey and Brooklyn, it's a critical gateway into this busy metropolis. One which trains must access. Today, alongside tons of cargo, Professor Eric Lima is experiencing an unrivaled view of the railway.
Oh man, we're on the front of a diesel train right now. The power on this thing is amazing. This freight service is huge for New York.
But getting locomotives into Staten Island means overcoming a tricky geographical problem.
It's the artery that brings all of the goods and services that we use on a daily basis, and we don't think about it when we're in the city, but New York City is completely surrounded by water. So for trains, this is easier said than done.
The stretch of water separating Staten Island from New Jersey, known as the Arthur Kill, may only measure around 170 meters across. But it's packed with boats.
This is an extremely busy waterway. There are thousands of boats that go through. And if you're going to have a railway across, you're going to have clearance for those boats to go under.
For a pedestrian or a car bridge, getting this clearance is no problem, as rubber tires and grippy soles can cope with an incline. Whereas steel-wheeled trains faced with a quick ascent get themselves into a spin. However, in 1959, the Baltimore and Ohio Railroad got round this problem with a monumental solution.
Wow, this is amazing. It's the world's largest lift bridge, the Arthur Kill.
But it's this bridge's extraordinary actions, rather than its colossal scale, that makes the Arthur Kill Bridge a standout structure.
I mean, that's an engineering marvel.
With a lift span of 170 meters, the Arthur Kill is the longest single-span vertical lift bridge in the world. When lowered for trains, it clears the water by 9 meters, but when raised, the span towers 41 meters high, leaving clearance for even the biggest ships.
Over here at the AK Bridge, we have the bridge drop scheduled for 9:45 a.m. You see any problems with that as far as vessel traffic goes?
But for Supervisor of Structures Ryan J. Wagner, it's not all plain sailing. To minimize disruption, the bridge can only be lowered 3 times a day, for just half an hour.
Okay, yeah, I see there. She's coming northbound, right? I'll call when I know she's clear, all right? Okay, Roger, will do. For our bridge drops here, we have to coordinate with the Coast Guard based on the tremendous amount of vessel traffic coming through the Arthur Kill Channel. We have about a half an hour time frame to get the train over and then to have the bridge back in the fully open position.
Lowering and raising a 2,000-ton lift span in such a short window requires supersized engineering. The bridge is fitted with a powerful system of counterweights and cables, driven by motors installed at the top of each tower.
Security, 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 AK Railroad Bridge coming to a close. Security, 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 AK Railroad Bridge coming to a close.
With all shipping being kept at bay, Ryan is putting this cutting-edge technology into action.
I've enabled the controls. That's enabled power to go to both drive motors. Once the drive motors are fully energized, I give the command for the bridge to go into the span seated position, and then the bridge starts coming down.
All right, here we go. It's starting.
The concrete-filled steel boxes used as counterweights each weigh a whopping 1,000 tons.
You can see the counterweights moving up right now in the perfect balance to the bridge that's coming down. You really want the bridge to come down exactly level. Both the motors have to work simultaneously, and so that there's no skew, so that the trains can go across, and then we can go across.
After just 2.5 minutes, the span enters its final leveling, a critical phase demanding millimeter precision.
So right now you have the bridge going through its skew correction system. We have a variety of sensors that are basically detecting all kinds of positions of gearing, physical track structure like the rails.
If the tracks don't line up, the trains will miss their crucial slot.
If all those checks are not correct, the dispatcher will not be able to allow a train to pass over the bridge. That causes a variety of issues. Train delays, it impacts vessel traffic because now we have the bridge seated and it cuts into our half-an-hour time frame.
With the bridge successfully locked, now the goods trains and Eric can carry on their journey.
All right, we saw it come down, and now we get the pleasure of actually going across it. What a piece of engineering. I'm looking at it now. I see the giant counterweights above. We're on it seamlessly. You can hear the banging and the clashing, and I see the water underneath. What a brilliant bridge. It's really hard to imagine that this is actually 100 feet higher in the air on a normal basis.
The 170-meter shortcut between New Jersey and Staten Island takes a matter of seconds. The race is now on to get the waterway moving.
Roger. So right now we're starting the process for the bridge opening. You have the warning indication to notify anybody that's on the span that the bridge is going to be opening.
Ryan and his team now have less than 3 minutes to open this impossible bridge.
See the counterweight coming down right here, right now. So at this point now, the span and the counterweight are approximately the same elevation.
Over 50 years after it first came into operation, the Arthur Kill Bridge still manages to return to its open position, bang on schedule.
Every day, there's always something new to be learned. There's always something that can be improved upon in terms of its operation to make it more efficient. Yeah, it's certainly something that I enjoy working with.
Every day, the brilliant mechanics of this towering bridge allow tons of freight to be carried in and out of Staten Island.
Without it, there would be no crossing. But with this bridge, the train just went right across. It seems so simple, and yet it's an engineering marvel, and it's really, really gratifying to see it work.
Picture battling rocky terrain and near vertical slopes for years on end. That's what it takes to complete a mountain railway. But before you celebrate, consider running it when winter descends. This can be a very different story. California's Sierra Nevada mountains, facing up to 20 meters of snow each year. It would seem like the last place on Earth to build a railway. However, in the late 19th century, the pioneers of California's Central Pacific Railroad thought otherwise. The railway was built to connect San Francisco to Utah via the Sierra Nevadas. By 1869, the section to Reno was almost complete. But there was still one major hurdle to overcome, as engineer Chris Potts is finding out.
This is Donner Pass, and this summit stood as the last major obstacle for the Central Pacific Railroad for joining California with the East.
Named after George Donner, the leader of a settler group, this 2,000-meter-high pass has an ominous history. During the winter of 1846, the traveling party became trapped by deep snow. After supplies ran out, to survive, they resorted to cannibalism. 24 years later, despite the evidence of impassable snowfall, the pioneering rail engineers pressed on.
Theodore D. Judah, the chief engineer for Central Pacific, thought that the weather up here would be no match for his railroad. Unfortunately, he severely underestimated the power of nature. Shortly after the completion of their railroad in 1870, many miles were lost under the snow, and it was deemed impassable.
Traditional snowplows relied on the momentum of the train. and a wedge-shaped nose, which works a treat until the snow deepens and turns to ice. With no machinery to tackle deep drifts, Judah built 40 miles of snow sheds to protect the track. But these smoke-filled tunnels were a temporary fix. Finally, in 1883, Canadian inventor Orange Jull provided a solution with a groundbreaking machine. The rotary snowplow. A truly monumental snow battling solution.
This absolute monster of engineering is the last word in snow clearance. If there's a serious snowdrift, this is what the railroad rolls out. Amazing.
Today, the conditions may be fair, but riding this iconic machine is a once-in-a-lifetime opportunity.
This machine runs off of 1,500 horsepower, operated by that B unit right behind us. This plow can clear massive amounts of snow in minutes. What a feat of engineering. Absolutely amazing.
Unlike those traditional wedge-nosed snowplows, Jull's machine relied on an entirely different mechanism.
This fan works like a giant corkscrew. It cuts away at the ice bit by bit, and what it does is it turns the snow into a fine powder, and then through the centrifugal force, shoots it out through the top in either direction.
With Jull's 12-foot fan able to tackle even the worst build-up, it would revolutionize snow clearance.
So not only could this snowplow move more snow than traditional methods, it was also much safer. Not needing the momentum that more traditional methods needed, this was able to operate for longer distances and at lower speeds, meaning there was less of a chance that this would derail. Shortly after its introduction, the rotary snowplow proved itself time and time again in the most severe weather conditions.
In the winter of 1952, Smart Ridge near Donner Pass experienced a huge blizzard. The city of San Francisco streamliner was buried in around 5 meters of snow, trapping over 200 passengers. Although it took 3 days, no less than 4 rotary plows finally reached the train, saving all but 2 of those on board.
Since its introduction in 1870, the rotary snowplow has fought the worst weather and won. It truly is the ultimate snow clearing machine.
History's locomotives have achieved great things. From the pioneering days of steam to the efficiency of electric and the mighty modern-day diesels. All have made their own mark, but have one thing in common. They struggle on anything steep. It takes a very special railway to climb mountains. On the wild west coast of Britain lies the spectacular Snowdonia National Park, for centuries a mecca for climbers. At the centre of it all, the summit everyone wants to ascend. Mount Snowdon. But at over 1,000 meters tall, these stunning views were once reserved only for the brave. At the end of the 19th century, however, one man decided he wasn't content with merely hiking to the top. He wanted to conquer the tallest mountain in Wales by train. Snowdon Mountain Railway has been clawing its way through the clouds for more than 120 years.
Engineer 1, Snowdon 1.
Mike, pass the message, mate.
Yeah, just to confirm, I believe number 5 is going out first.
This morning, they're preparing the historic rolling stock for another remarkable attempt on the summit. It's been an all-night process.
It's always a busy time prepping for the day. So steam locomotives, they've been in steam overnight with a fireman on watch.
Some of the locomotives are over 120 years old, and they're facing a seemingly impossible near 8-kilometre climb.
The terrain is difficult. The steepest gradient on the mountain is 1 in 5.5. For every 5.5 metres, the track rises a metre. So it's quite steep.
This daring adventure is the brainchild of one man. Railway tycoon Richard Moon had a vision of bringing the mountain to the masses. Today, fireman Elizabeth Partridge, driver Robert Henry Jones, and general manager Alan Kendall are all following in Moon's footsteps as they and a carriage full of adventurous tourists attempt the journey to the top.
Okay, ladies and gentlemen, can I have tickets, please?
But it's far from certain they'll make it all the way.
We are on wind warnings today. If wind speed increases on the mountain, we may be forced to stop at Rocky Valley, okay?
There'd always been an interest in getting to the top of the mountain for 300 years, really, and prior to the railway, people walked and hiked and climbed, and also went up by donkey and horse.
Moon's proposed route started from the base of the mountain, passing a sheltered rocky outcrop to traverse a 1-kilometre-long exposed ridge, before ascending the last 200 metres to the summit. But no traditional railway could ever provide enough traction to scale the steep incline. A fact clear to current senior engineering manager Mike Robert Shaw, down below in the yard.
Well, in a normal railway, all the traction and braking forces is carried out by the steel wheel on the steel rail. In our case, because the gradients are so steep, you get no adhesion between the steel wheel and the steel rail, and the locomotive would just sit and spin or slide backwards.
Mobile 5 to Snowdon 1, stop at Hebron.
The consequences of slipping back down such a gradient are unthinkable. But there was a possible solution, one that had been perfected by a Swiss engineer just a few years before.
The absolute only option to go to the summit was a rack and pinion railway.
Unlike a traditional train where the power is transferred down an axle to the wheels, Moon's Snowdon locomotives have a cog on the axle, which connects with a toothed rack running between the rails, meaning getting enough grip is no longer a problem.
Well, this is a rack and pinion railway. This part is the rack, and these are the pinions. And on the main track, there's a pair of racks, and on the locomotive, there's 2 driven axles, each with a pair of pinions. So the pinion, there's always 2 teeth fully engaged in the rack.
It was a brilliantly simple solution to a once impossible problem. But whilst the system can cope with the gradient, the unforgiving mountain climate is another matter.
The weather on Snowdon is always a challenge all the year round, and particularly in the winter. We are in July. You can see the cloud coming in. You can feel the temperature drop.
Mobile 5 to Snowdon 1, do we have an idea on the current wind readings?
Snowdon 1, Mobile 5, yeah, the last wind reading at 45 was 45.1.
If the weather deteriorates today, the train will be forced to terminate some distance below the legendary summit. Cloud and mist have shrouded the peak just as they did on the railway's opening on the 6th of April, 1896. After successfully reaching the summit, locomotive number 1 started its descent, but having lost control, jumped off the rack. The crew leapt clear, but the runaway engine derailed and fell over the side of the mountain. Some way below, a climbing group told of looking up only to see a steam locomotive falling out of the cloud. After an inquiry, additional gripper rails fixed around the track's rack would lock the trains firmly in place. Today, it's an anxious wait for crew and passengers, while control decides if the weather is too severe to continue to the peak.
You may proceed up to the summit on 09, mate.
Mobile 5 to Snowdon 1, proceeding up to the summit on 09.
It's good news. But first, the train must navigate the steepest part of the track.
The upper mountain is a serious gradient, 1 in 5. We're currently travelling on an original locomotive from 1896. You can look out of the window and you can see the gradient behind you. You can appreciate just how hard that boiler has to work and the pressures that it has to create.
The steep gradient means an ordinary boiler would be unable to cope. A traditional steam engine boiler consists of a cylinder filled with water surrounding a series of pipes. All very good for travelling on a flat line. But if you're trying to climb a mountain, as the train tilts, the changing water level exposes the pipes, with potentially calamitous consequences. So how can the danger be averted?
So this is one of our locomotives that we're doing some work on. And this part here is the boiler. And as you can see, it's inclined forward at an angle. And that's so that when the locomotive goes on the mountain and the chassis goes upwards at the front, the boiler becomes level.
It's yet another brilliant solution that means Richard Moon's mountain dream can be accomplished.
Mobile 5 to Snowdon 1 and the summit past the 1 in 5.
As once again, this astonishing train achieves its mission.
Okay, ladies and gentlemen, welcome to the summit. Be very careful, there are high winds today. Mind the gap as you come off and enjoy your stay. Thank you very much.
So here we are, it's the end of July, unbelievably. We're at the summit of Snowdon. You get a real sense of why the original engineering team wanted to build a mountain railway to the top of the tallest mountain. It was not only a challenge, it was something they'd go down in history for. So, hats off to the Victorians.
On a clear day from this station at the rooftop of Wales, it's possible to see England, Scotland and Ireland. Richard Moon's 19th century vision created the journey of a lifetime. Expert Krzysztof Kowalczyk is in remote northern Poland, where in the mid-1800s engineers decided to build a series of canals to join the seaport of Elbląg with the rich timber region of Ostróda.
Since 16th centuries, trees from this area was very expensive because there was the best raw material for the mast to the ships.
But standing in the way was a 10-kilometer uphill stretch. A total rise of 100 meters.
On this distance, on this difference of level, the logs was impossible because there were 32 logs on the distance 10 kilometers. Logs take too much water and there was too many logs.
It was down to Prussian engineer Georg Jakob Stenker to find an answer to this seemingly impossible problem. And today, 150 years later, skipper Bartek is about to face the obstacle that stood in his way.
Jak powoli się zbliżamy.
And Stenker's extraordinary solution.
It is the most strange railway in the world. This is not for any kind of train. This is for boat, for ships. It's only one working in the world, system like this.
I już wtedy pojedziemy, nie popłyniemy, a pojedziemy.
Georg Stenker created a railway capable of lifting boats out of the water and carrying them up and down hills.
Wózek przetransportuje nas na drugą stronę górki.
There are two parallel sets of track, each with a wagon capable of holding a 30-metre-long vessel. The two carriages are connected by a looped steel cable.
Taki wózek waży około 20 ton.
This cable is, you can see, have to be very strong to pull a carriage with a ship which is weight about 50 tons. It's a lot.
Są to wózki oryginalne.
This amazing solution to connect these canals, there was just slipway. Slipway like this, with dry hill. There is one canal, another one canal is about 20 meters lower, and that was the great solution.
5 of these boat railways sit along the 10-kilometre journey, lifting the boats in a series of steps to the summit.
When the ship coming on the carriage and connect to the carriage, the man from the ship is coming and ring the bell. So operator know that he is ready. When he is ready and everything is okay, operator giving the signal with the bell to the operator in a machine place.
And it's no ordinary machine.
That's water wheel. That's an engine. That's giving the power for all this system for pulling the 50-ton ships 20 meters up to the next canal.
Cleverly, Stenker's railway harnessed the massive potential energy of waterways themselves.
You can feel the vibration, how it's working. It's amazing this building still exists. It's not destroyed by this vibration. You see, in one of the swing is capacity about 1 ton of water. So in one moment, 3 are full. So 3 tons of water is turning this wheel. Wheel is about 8-meter dimension. It's more than 4 meters wide. You never saw a bigger water wheel than this.
The wheel is used to wind the massive lifting cable.
This is the heart of the system. You can see this drum with the line. This is one line. Everything working with power of water. Miracle! That's amazing.
Each wagon is counterbalanced by another, travelling simultaneously in the other direction.
Jesteśmy gotowi do przeprawienia przez górę.
This ingenious system can transport skipper Bartek and his boat over each of the 5 inclines in only 30 minutes.
Właśnie, musimy się już powoli na wodzie. Zostawiamy wózek za sobą.
From its opening in 1860, the incline lift system transformed the region. It was now 5 times quicker to transport timber to the coast, and the Elblag Canal became one of the longest trade routes in Poland. As the road network grew, however, it fell from favour, until one forward-thinking man intervened.
He named Adolf Tetzlaff. Adolf Tetzlaff have 8 children with first wife. With second wife, he have also 8 children. He have to find idea how to earn the money. He found idea to bring the tourists on the ships. And he rebuilt one ship for tourists and start to transport tourists on canal. And that was a very good idea.
Today, tens of thousands of tourists every year ride Georg Stenker's impossible boat railway.
Engineer Georg Jakob Stenker, thanks him, we have this original. It's absolutely amazing because it's one in the world and it's still working.